Welcome to Tech Time Plus. I'm your host, Paul Jakovic. Joining me today is Brent Rupert. He's a subject matter expert for the 3.9-liter LS and a Thunderbird at the Hotline. In today's show, we'll be reviewing torque-based electronic throttle control, or ETC. The system is based on the customer torque requested, which is compared to the estimated torque output. We'll review the inputs to the PCM, the internal PCM hardware and software, the outputs, and the failure mode effect management, or FMEM, commonly called limp home mode. We'll also review how to perform a coil on plug stress test and show you good and bad coil patterns. We've got a cool tool and a tool giveaway. Brent, what is the ETC?
The ETC is a system where the throttle is completely controlled by the PCM. There is no cable linking the accelerator pedal to the throttle body. The PCM uses driver inputs from the accelerator pedal assembly through 3 accelerator pedal sensors. The PCM then analyzes the inputs and adjusts a DC motor on the throttle body by duty cycle. The throttle body has a single throttle position sensor assembly that includes 2 throttle position sensors, or TPs, to let the PCM know how far the throttle plate is open. There is no throttle cable. The ETC allows for better fuel economy and better torque output control.
Boy, that sure seems complicated.
Paul, let me show you. I've got a schematic that might help. Let's start from the left and work across the schematic. Here's an overview of the system. You have the pedal assembly, which includes the APP sensor. There's the sensor inputs to the PCM itself with its internal components, and the throttle body assembly. We have the AP input for driver request. An input basically tells us how far the pedal is being pushed. Here's an image of the accelerator pedal. As I've mentioned before, there are 3 AP sensors that input to the PCM. 2 are rising signals, and 1 is falling signal. Here's a graph that depicts this. The AP sensors operate on a 5-volt reference voltage. The PCM uses the crossing of the signals to determine the validity of the signals. APP2 and APP3 are rising signals. APP1 is a falling signal. You can lose one of the inputs and the vehicle will still drive normally. If 2 or 3 signals are lost, the PCM will go into FMEM, or failure mode effect management. This is also referred to as limp home mode. We'll cover this in detail later. For operating voltages, you should reference pinpoint test DK in the 2005 PCD manual. You'll want to use the version on the PTS website for the most current information.
We've talked about the AP sensors, but what other sensor inputs are used by the ETC system?
Paul, there are several. I'll break them down into different areas. In reviewing the schematic, we have both engine control inputs and vehicle speed inputs to the PCM. The combination of these inputs lets the PCM know engine torque input and torque output. The engine sensors are used to define what the engine is doing. There's the mass airflow, or MAF sensor, which is used to determine engine load. The EGR system management, or ESM, which is a combination of the DPFE, MAP, calculated barometric pressure, and EGR vacuum regulator. A little side note on this one. If you want to verify that the ESM barometer information is correct, use TSB 05-03-01. The TSB compares map voltage to barometer information using a reference chart. It also has you compare barometer hertz to altitude. And last but not least, the crank position sensor. This is used to determine engine output, or RPM. The PCM uses these inputs to determine what the driver is requesting, what the PCM is commanding, and how the engine is reacting to these commands. Now for the sensors that determine torque output to the wheels. Depending on application, the PCM uses 2 of the following sensors to determine the output. you have the turbine shaft speed sensor, the output shaft speed sensor, the vehicle speed sensor, which communicates its signal from ABS module through the CAN network, and the wheel speed sensor, which also communicates its signal from the ABS module.
The PCM has several different components. The three main pieces are the CPU, which has software called the Independent Plausibility Check, or IPC, the eQuizzer, which checks the system, and the throttle plate position controller.
The IPC looks at driver demand and torque output. The IPC adjusts the output to meet the driver's input request. The PCM has a redundant processor called the eQuizzer. The eQuizzer monitors PCM inputs and outputs. The eQuizzer checks the IPC software once a second, and if there are any discrepancies, it goes into FMEM or limp home mode. The eQuizzer defaults to the FMEM mode anytime a fault is detected.
Next is the throttle plate position controller. The controller communicates with the CPU. The controller then communicates with the H driver or H bridge. The H driver duty cycles the throttle position motor to the proper desired throttle position. The PIDs for this function are the ETC actual and ETC desired.
Last, we have the throttle body. There are two TP sensors that are incorporated into one assembly. This is mounted to the throttle body along with the throttle plate motor. Here's an image of the throttle body. On the one side is the DC throttle motor, and the other is the TP sensor. The TP sensors operate on a 5-volt reference voltage. There is a rising and falling voltage signal that does cross. The rising signal will level off at approximately 49 degrees from the throttle hard stop or closed throttle position. The falling signal is used by the CPU for control strategy. Both TP signals are sent to the PCM, the eQuizzer, and the throttle plate position controller, or TPPC. The duty cycle commanded from the TPPC is compared to the throttle plate position to determine if there is a fault in the system. The system will then go into FMEM.
Brent, we've mentioned failure mode and effect management, or FMEM. Can you explain exactly what this is?
Paul, FMEM, or limp mode, is a default strategy initiated if the system is operated beyond its design parameters. The eQuizzer is the controller of this strategy check. The eQuizzer has several default modes, which varies from no effect on drivability to disabling the engine. The FMEM effects and failure modes are no effect, disabled speed control, RPM guard with pedal follower, RPM guard with default throttle, RPM guard with high forced idle, and finally, engine shutdown.
Brett, can you go into the details of these FMEM modes?
Sure, no problem. There are 6 modes you need to know about. The first mode would cause no effect on drivability. You could see the ETC lamp or the wrench lamp illuminated, but there will be no drivability concerns. This mode is caused by a loss of a redundant system or non-critical input. The second mode is disabled speed control. In this mode, the ETC would operate normally. None of the indicator lamps would be on. The third, fourth, and fifth modes are somewhat related. The modes are called RPM guard with pedal follower, RPM guard with default throttle, and RPM guard with high forced idle. In these modes, the RPM will be controlled by limiting spark and fuel. Depending upon the fault, the vehicle may go into limp home mode. These modes could be caused by a loss of critical sensor input to the PCM, or the PCM failing itself, no throttle position input, a malfunctioning throttle plate position sensor, an electric throttle body fault, or the loss of 2 or more AP inputs. In these modes, depending on the fault, you may have limited throttle control, where you step on the accelerator and the vehicle accelerates, but only with limited RPM. Or you could find you have a fixed RPM with no throttle response. In RPM guard modes, your ETC and mill lights will be illuminated, and you will set a code P2106, P2110, or P2104. The sixth and final mode is the engine shutdown mode. This is the result of a processor detecting a significant fault. It will result in the fuel injectors being disabled, the ETC and mill lamps being illuminated, and code P2105 being set.
Brent, when the PCM goes into FMEM or limp home mode, what are the critical areas to remember?
When the PCM goes into FMEM and you see codes P2106, P2104, or P2110, you should have additional codes that caused the PCM to go into FMEM. These codes should be addressed first. Remember, a sensor can be hardwired to another module and communicated to the PCM with network communications. You'll want to pull codes from all of the network modules. The best tools to do this are the WDS and the Portable Diagnostic Software, or PDS. If you get a P2104, P2105, P2106, or P2110 alone, you should review current TSBs or SSMs. If there is no additional information available, contact the hotline for further assistance.
If there's an intermittent concern, you'll want to make a VDR recording. The VDR has the fastest refresh rate of all the scan tools, and you'll be able to see if the signal is breaking up. Also, zoom in on the playback of the recording. What looks like a smooth line in the normal setting may not be when you zoom in. I'll show you how to do this later. Brent, after verifying the customer's concern, what would be the next step of our diagnosis?
You should run OASIS to see if there are any messages that applies to the customer's concern. There are some TSBs and SSMs available for the ETB. Some include updating the PCM calibration.
Hey, I read an electronic field communication on that. The communication number is EFC 0501038. It indicated that starting June 1st, 2005, the PCM should only be updated if there is a TSB or other written communication. The TSB, starting with 2006 model year vehicles, will include the proper labor operation for the recalibration. To check for an updated calibration, the technician can run OASIS with the VIN and symptom code or diagnostic trouble code. The generic labor time code 12650D84 will no longer be used.
Next, you would want to perform a self-test. You'll want to follow the pinpoint tests for the codes you retrieve. The electronic throttle codes are P0606 or any P060 type codes, which indicates a potential processor problem. P2106, which is for the ETC FMEM, sensor or sensor circuit fault, MAF, a single TP concern, or a CKP, TSS, VSS, stuck throttle, or throttle actuator circuit concern. P2110, which indicates that both TP sensors failed, or a throttle plate position controller fault. P2104, which indicates that 2 or 3 APP sensors failed. P2105, which occurs when an eQuizer fault is detected. And U0300, which is caused by mismatched software between the CPU independent plausibility check, eQuizer, and the throttle plate position controller. The APP DTCs are P2122, P2123, P2127, P2128, P2132, and P2133 for the APP sensor circuit continuity. P2121, P2126, and P2131 for the APP range or performance. P2138, P2140, P2139 for the APP to APP sensors do not correlate. The throttle position sensor codes are P0122, P0123, P0222, and P0223 for the TP circuit continuity test. P0121 and P0221 for the TP range or performance. P2135 for the TP1 to TP2 sensor correlation. Throttle plate controller check codes are P2107 for the processor test, P2111 for the throttle actuator stuck open, P2112 for the throttle actuator stuck closed, P2100 for the throttle actuator circuit open, shorted to power, or shorted to ground, P2101 for the throttle actuator range or performance, and P2072 for the throttle body ice blockage.
Brent, what test are you seeing the most calls on? What are we having difficulties with?
The sweep test in DK1 is the one that is sometimes hard to read. You really have to zoom in on the APP and TP signal to verify a concern with a sensor. Also, we get a lot of calls on the COP stress test.
Let's head over to the LS so we can demonstrate how to run these tests.
Sounds good.
I've got the LS already connected to the WDS. The vehicle has been ID'd, and I have the data logger open to the PID selection.
The PIDs needed to start the sweep test are APP1, APP2, APP3, ETC-ACC, ETC actual, ETC-DSD, ETC desired, TP1, and TP2. The ETC PIDs are for the air bypass function. Now hit the tick button and go into data logger. You want to hit the movie camera to record when you step on the accelerator pedal and release it. Now go into playback and zoom in on the APP and TP PIDs. You're looking for any spikes or opens in the recording. If the PID signal comes in clean to the PCM will then drive the DC motor on the throttle body to open the throttle plate. We'll then see TPs 1 and 2 do their sweep test back to the PCM. If these signals come in clean, then the PCM can command advance of fuel delivery, spark, and timing. One thing to remember, the eQuizer is monitoring the system once per second. If there is a reading out of specifications, the eQuizer will go into FMEM or limp mode.
What other concerns have you seen that could cause the PCM to go into FMEM?
There have been some concerns with radio frequency interference, or RFI. The RFI may be coming from a coil on plug, or COP. The symptom may be a misfire concern under acceleration, or the ETC lamp illuminated in the dash, along with codes in the system. The customer may also indicate that the vehicle is not performing properly if it is in FMEM. You'll see this happen on the TP or MAF readings. You'll want to use the VDR when trying to test for this. When reviewing the data logger, you need to zoom in on the TP sensors. TSB 04-16-01 instructs you on how to perform the COP stress test. You'll need to order the WDS COP kit part number 418-FS528 to perform this test. The first thing you need to do is perform a self-test to see if there is a misfire code. If there is, you'll want to perform the COP stress test on that cylinder. If there are no codes, next perform a power balance to identify the cylinder. If the power balance test does not show anything at an idle, try to brake torque the engine. After identifying the cylinder, you'll want to perform the COP stress test. From the main screen, select the toolbox on the top left. A new menu will appear. Select Oscilloscope, then select the tick button. The oscilloscope will then open. Select Channel 3. A drop-down menu will open with Auto None and Manual. Select Auto None, and another drop-down menu will appear. At the bottom of the menu is COP stress test. Select this, and the WDS will automatically configure the oscilloscope. Attach the WDS COP lead to the C3 connector on the WDS. Next, with the key off, remove the suspect COP, leaving it connected to the wiring harness. Attach the COP WS lead so the lead is on the top of the coil with the connector between the pointed tips of the lead. Turn the coil over, making sure it does not arc to anything. You may want to wrap a clean shop cloth around the COP to prevent it from moving.
Now disconnect the fuel injector to prevent raw fuel from going into the cylinder. If you don't disconnect the injector, it could damage the catalytic converter.
Hey, Paul, can you reach in and start the engine?
No problem.
Check to ensure that the COP is not arcing. If the COP is arcing, shut the engine off and reposition the COP. With the engine running, touch the red man on the right side of the screen. Wait for the red man to start running and a pattern will appear. Here is an example of a good reading. Notice how the pattern goes down and comes back up relatively smooth. Here's a pattern I saved earlier. This COP is one that is just starting to go bad. Notice how the signal is not as smooth as the good one. With this COP, you may have an intermittent misfire. The last one is a COP that is bad. Notice the pattern is all wiggly. This COP would give you a consistent misfire. You want to replace the COP and retest the vehicle under the same conditions as the customer is experiencing the concern.
Brent, thanks for demonstrating these tests.
No problem.
Let's head on back over to the tech time desk.
That coil unplug stress test worked out real well.
Yeah, we have to thank Robert when we get back to the hotline. You know what that means? It's time for Cool Tools. Today's cool tool is the Flex Probe Kit tool number NUD 105R025C. This is something that every diagnostic technician should have in their box. It offers technicians the ability to probe Ford connectors using the proper size mating terminal. Probe tips plug into the standard banana jack test leads for ease of use with all automotive meters. The kit contains a package of 2 stackable banana jack patch cords, 4 feet in length, and color-coded red and black. In addition, there are an assortment of male and female probes from 60 thousandths to 2.30 millimeters. This is good for everything from a EEC5 to a 7.3 liter and 6 liter diesel. This toolkit is available through the RTTP website for $90. Check it out and order yours today. Now for our tool giveaway. Today's tool is the NUD 400-018, an 8-inch 90-degree diagnostic connector. This item was engineered and introduced as a result of technician feedback in the field. The right angle adapter can be used with Ford-approved diagnostic tools like the WDS, NGS, NGS Plus, PDS, and the VDR. This thing makes it a lot easier to access some of those tight locations with your diagnostic tools. This tool is listed on the RTTP website for $45.77. So hit your flag button now and you'll be entered into a drawing for these tools. Well, that's our show for today. We hope this information will help you in your diagnosing and repairing of vehicles. Thanks again for tuning in. Hey, thanks for your help.